I'll start today's. So today, mostly what I'll do is I'll just recap eligibility traces. Uh, what sir has told in this week's lecture, those things I'll recap. And after that, what I'll do is I'll recap Q-learning and SARSA, which we did last week in the last week tutorial. And I'll show you a code on how for a grid world, code for grid world. Yeah. So how we implement Q learning in SARSA for random for stochastic grid world. I think we did a non-stochastic purely deterministic grid world where the environment didn't have any stochasticity in it. So if you took an action of going left, then you would go left in the grid world. If you took an action of going up, you would go up in the grid world. And you needed to reach to the endpoints of the grid. So this was our grid world when we did value iteration and policy iteration. We'll do the same grid world, a bigger grid with some parts of the grid where you'll be penalized to go and some parts of the grid where like you randomly generate somewhere and you have to reach to the goal point, but you have paths where you'll be penalized if you go through that. So you need to like it's like an obstacle. So you need to overcome that obstacle and reach your goal. So we'll do that grid world under the stochastic setting for Q learning and SARSA. For we'll do it as a code. So yeah. So first let me just recap eligibility traces. So yeah, I hope I am audible and also I hope I'm audible and also my screen is visible, right? Okay, yeah, sure. Thanks, Anish. Okay, so yeah, feel free to stop me anywhere you have any doubt. So last class we discussed about TD0. Today we'll go to TD lambda. So first for so first we'll know that we want the returns given that we are at a state at time t we are at state s. We want to know like what are the returns I could get when I so what are the returns I could get. So return at time t for Monte Carlo was RT plus 1 plus gamma RT plus 2 plus gamma square RT plus 3 plus so on gamma t minus t minus 1, or is it capital T minus t minus 1? It's capital T minus t minus 1, capital T minus t minus 1 R. So this assuming that RT is where your episode ends. So RT is a terminal state, but that RT is not deterministic, it's stochastic. So you don't know when RT is, but you know that if you reach there, you will your episode is ended. RT could be deterministic, it doesn't mean that it cannot be deterministic, but it also might be stochastic. Okay, so next we have returns, one step return. So this I'll write it as TD. Okay, TD not 1, TD0 was 1 step. Okay, so I'll write it as GT1. So this you would calculate by RT1 plus gamma into VT into ST plus 1. Yeah, so this what you would do is you would just play it one time and you would use your previous value iterate for the next state for the whole rest of this thing, like previous estimated value function, you would use that and you would update the output. So for one step return, what you would do is you would play it one step and you would use your previous estimated value states and update the return. So similarly you would have G2, which is RT plus 1 plus gamma RT plus 2 plus ET plus 2 ET plus 1 S T plus 2. So here you're in ST, you take 2 steps forward and then you use your value function in ST, which is the same value function that you have at ST plus 1. We have not updated ST plus 1, we have updated ST. Look at the 2 steps and then update using the 2 steps that you have done. So this is GT. So on you can write the nth step return. The nth step return will be given by RT plus 1 plus gamma RT plus 2 plus 1 gamma power n. Okay, gamma power n minus 1 RT plus n plus gamma power n T plus n minus 1 S T plus n. So this is your nth step return. So now you use these nth step returns to update your value function at whatever step till whatever step you are calculating the nth step return. So if you are calculating till the nth step the return, then you wait till you have generated a trajectory till n steps. Find that new updated V, update it for Vs plus T. So yeah, so now you have offline and online policies. So yeah, so delta Vt of S is your update. So this is what you update. So delta Vt of S is basically Vt plus 1 S minus Vs. So what is your value function at Tth instant? And then so Vt plus 1, your new estimated value function is your Vt minus Vt plus the change in your value function, since now you have explored a new state. So given the trajectory, given that you have explored new state, that is the update that you have to make in your value function. The same thing can be done for the Q function, but for Q function you need to be careful. I think this type of computation you have also seen before with Q learning in SARSA, where you update in TD0 and all, where you update your value functions based on the trajectories which have been given. Okay, so in online method what you do is, in online method you have Vt plus 1 of S is equal to, okay, so yeah, it's basically Vt plus 1 of S is equal to Vt of S minus delta, okay, plus delta Vt of S. So your next step estimate of the value function is the old estimate plus your delta Vt. This delta Vt of S, as we have seen in TD0 algorithm, it was alpha into. This alpha is for the convergence, which needed to belong to, does not belong to L1 space, but belongs to the L2 space. So L1 is the summation of all alphas. So here it's actually alpha t, but yeah, it's fine. So this thing, and Gtn minus Vts. So what does this Gtn says that delta of Vts is actually 0 for E less than, okay, so maybe I'll write this more clearly. Okay, so delta Vts is equal to 0 if T is less than E plus N, and its Gtn, it's alpha T minus V into Gtn minus Vts if T is equal to T plus N. So here T is a random variable, I could have just updated, yeah, so this is the alternate, so you are updating over T. So T is your actual time instant what you are. T prime is the present time instant currently which you are. So if T prime, so now if T prime is less than T plus nth one, you don't have any update. But once you reach the nth state from T prime, once you go there, you update it using all the using the nth step reward. This is clear. Okay, so next I'll go into the backward in the forward view. So eligibility case. For the eligibility case. This is actually a 3D lambda algorithm where instead of using any number of nth return, like nth return, so nth total return, what you are doing is you are basically taking, you're weighting all the different returns, like you have first return, second return, third return, fourth return, fifth step return, sixth step return. You're taking all those and you are weighting them to get an average out of them. So one of the example is you could do the first return plus the second return by 2. This is one example that you could do. But yeah, so the lambda comes into play when GT1 plus lambda into GT2. So this is not GT lambda, this is some GT arbitrary lambda here. This is GT lambda. GT2 plus lambda square GT2 plus 1. Now to make the summation, I think you must have gone to the lecture. You put 1 minus lambda in GT1 plus lambda GT2 plus lambda square GT2. So the weighted sum is lambda power n by lambda 1 minus lambda into lambda power n. So what you get is 1 minus lambda into summation I equal to 1 to t minus 1 lambda. Okay, this first initially it goes to infinity. Lambda power I minus 1 dt I. So, but since you have a terminating state, you can't go till infinity. So you just go till the state which it has terminated. I is equal to 1 to e minus t lambda I minus 1 gti. But then you have the remaining return is the same, because once it terminated, anytime you go back to it, it will always be 0. It will keep on being 0, 0, 0. So what you do is you just multiply t minus 1. So this multiplication is the whole term into g. So this is how you can update. So instead of using nth step return, you can use lambda, gt lambda to update. Now here for the forward view there is no offline and online mode. So in online mode what you do is the first time you cover n steps, you calculate the delta Vt, you update your value. You don't care whether you have reached the terminal state or not. In offline what you do is you wait till you have reached your terminal state, you collect all the different n delta Vts for different nth rewards, calculate all those, and then you sum it up. So for offline, your Vt plus, okay, this is not Vt plus 1, because now you are not updating in the next state, you are updating once the whole episode has terminated. For offline, what you get is V new of s is equal to V old of s plus summation equal to 0 to t delta Vt. So what you do is, when you reach state s, you look forward till it has terminated. You get one whole trajectory till the trajectory is terminated. Then for the first state, you go t plus n times, look at the gt, calculate the delta Vt, don't update it. Now you see when the next state, when the same state has occurred again. From there you go t plus n, you look at the gt, calculate delta Vt plus 1, or when the state was again observe, go n times forward. So look at that for the whole trajectory that you have generated once. All these delta VTs you calculate for the state. Now what you do is V nu s is equal to V old s plus summation t equal to 0 to delta VT of s. So delta VT of s would be 0. It's delta VT of s similarly defined as you define online case, but in the offline case what you're doing is you're just adding it up, you're calculating it, you're updating it once by adding it up. In online what you're doing is each and every time you're adding it, you keep on adding it. Yeah, I hope you guys don't have any doubts in offline and online mode for TD0 TD lambda. So I'll wait for 2 minutes here so that in case we have more. So next is forward view eligibility trace. Yeah, so I hope now you see that in forward view eligibility trace there is no offline and online method, because you need to wait for the whole trajectory. So you need the whole trajectory till the termination state for you to calculate GT lambda. I hope that is clear. Okay, so next is my backward view. In the backward view, I have eligibility trace. So what does eligibility trace mean is, suppose I get a reward in this instant and some event happens here and another event happens here. What I do is I assign a reward to it with the eligibility of this event happening. So this reward, I have no idea whether this reward happened because of this event happening or this event happening. So what eligibility trace does it finds a relation between how far back did that event occur, did that event cause my reward. So it's not, so eligibility trace is not just your previous state which totally affects your reward. It's that your long back nth step also could have affected that reward. So what you do is, but the weightage to the temporarily far away event is very less. The closer you are to the reward, the event which is temporarily close to the reward will have higher weight than this thing. So you assign a decreasing function for this, and once you reach the reward time, you check which has more credibility, you weight it according to that credibility. So this is the basic concept for eligibility trace. So now if there are multiple ways you could implement eligibility trace. So there is one which is accumulative. So suppose if that event again occurs here, so you could always add 1, and if suppose this is 0.2, you can always accumulate. Anytime that event occurs, you could increase it by 1. And what you could do is you could always maintain it at 1, this event. So that even if the next event occurs, just bump it up to 1 and leave it. Or you could bump it up such that your current eligibility trace you have plus 1. So suppose you have something less than, suppose you have eligibility trace which comes down to 0.3, and then the event again occurs. So bump it up to 1.3. Or you could do it such that it bumps up to just 1. So there are 2 ways in which you update the eligibility trace of this thing. So you use comma lambda. This lambda is for the TD lambda, this thing which you have minus 1 s if st not equal to s, gamma lambda minus 1 s plus 1 if st is equal to s. So this is known as the accumulative this. And the same thing here. What you can do is you can replace this with 1, like just change it to 1. If st is equal to s and the above part remains same, this is known as replacing trace. So this is how you update your eligibility trace, and then you put it to control this thing. Since I'm running short of time, I'll skip through those parts and I'll just go back to Q learning and SARSA. So if you guys have any doubts till now, you can ask me. Okay, so let's go to SARSA first. So why I am recapping SARSA and Q learning? Because I just wanted to show you the code for SARSA and Q learning, how those work out in stochastic setting, stochastic pattern setting, those stuff. So SARSA, which is an on policy algorithm. So that's an on policy. So yeah, so I'll just go through the steps of what is it. So first you start with an initialized Q. So you initialize Q s comma a for all states and actions, and then what you do is pick state s0, you're starting 0 at time t equal to 0. Next, what you do is you pick action AT in st. According to Q st comma dot, such that your epsilon greedy. You apply epsilon greedy. You could also apply softmax here. So this is the exploration part. Exploration part of your actions. Yeah. Then what you do is then you apply AT. The action that you have sampled using epsilon greedy or softmax, and once you have done that, you go to some st plus 1 and you get some reward rt plus 1. So you sample st plus 1 comma rt plus 1. Then what you do is you pick AT plus 1 according to Q st plus 1 comma dot. You just pick an next action. This is also based on epsilon. Now you update your Q st comma AT is equal to Q st comma AT plus alpha rt plus 1 plus comma Q st plus 1 comma AT plus 1 minus Q st comma AT. I hope SARSA is clear. If you guys have any doubt, you can ask me. So if you do this continuously, you will reach to the optimal policy. You'll reach to some optimal policy. And yeah. So I hope SARSA is clear. Now I'll explain Q learning. Okay, so Q learning also follows the same step. Start with initialize all the Qs in your state space and action space. Yeah, then pick state S0 at t equal to 0. Pick action AT in ST according to QST. Here again you have epsilon greedy or softmax. So now you don't need to again pick 80 based on epsilon gradient. You can just update your st comma 80 is equal to q st comma 80 plus alpha. Okay, now so you sample 80, get st plus 1 comma rt plus 1. Then now no need to again pick 80 plus 1 which you used to do in SARSA. That thing is not there in Q learning. You do alpha into rt plus 1 plus gamma max over all the actions that you can apply to st plus 1. U star. So this is st plus 1 comma a prime minus q st comma a. Yes, this is how you update here. Q learn. Okay, I hope this both is clear, because now I want to show a code SARSA and epsilon learning for grid world. I will set up a problem in that. So yeah, so if you guys have any doubt in this, you can ask. Yeah, stop sharing here. For this I need to show. Is my screen visible?
Yes, sir.
So thank you. So first, what I'll do is these are just the relevant libraries that I'll explain the problem statement what it is. So these are just NumPy and plotlibs and this kind of stuff which are generally. Okay. So what we'll do is in this section we'll implement SARSA and Q learning problem algorithms on a grid world navigation task. So I hope you know your grid world. Grid world which we did for value iteration and policy iteration, but that was very deterministic, so that was very easy. So what it is like you have a grid, your agent is in some place. If you take the action up, your agent would go up. If you down, left, right, whatever you take, they go down. So what is the endpoint of that agent to do is, it is assigned randomly some starting position. So it's randomly somewhere in the grid world it's put down. Now it needs to find the optimal policy so that it reaches its final end position, which is the goal position. So what you need to do is similarly what we did to value iteration and policy iteration. You need to find the optimal policy once the agent has reached any state. That's what you need to do. But now you need to use SARSA and Q learning to that. So first we'll take the actions. So down, up, left, right. These are the actions. I'll denote them. Then this is the grid world. I'll show what the grid world is in a minute. So we have a 17 by 23 grid. So yeah. So let me show this once. Okay. So now, so there is a goal state in this reward. So I want the agent to reach to the goal. Okay. And to add stochasticity to this setting, what we do is, with probability 0.2, agent takes a random action. So what does it mean is, even if you tell it to go up, with only 0.2 probability it will go up. With probability 0.2 it will not go up. So with probability 0.2 it will uniformly choose from going left, down or right. But that is not in your control. That is a stochasticity in the environment it has. I hope that is clear. And also, the another stochasticity it has is, there is a westerly wind blowing to the right. So there is a wind which is flowing from left to right. So hence, after each action that you take with 0.5 probability, it will just randomly move to one step right because of the wind that is blowing on the grid world from left to right. That also you have no control over. I hope these two stochastic problems, stochasticity in the environment, you have understood. If you have any doubt, you can ask me. So this is the problem statement. So you have an agent, you need to go to a goal from any random point. And the stochasticity in the agent is whenever you tell it to take an optimal action, which you have already pre-calculated, with pointed probability to take the optimal action, but with pointed probability to take some random action which is not optimal or which is not what you told it to take. And in the whole grid world, there is a wind blowing from left to right. So with 0.5 probability, it will just randomly go one step right, irrespective of whatever action you have chosen. Okay.
So what is the two, the 1 and 2 in the grid world?
I'll come to this. I'll just come to this. So let me just plot the grid world once, then you'll understand. So these are the reward functions. So take these as -2s and -1s. Okay. So they are reward functions. So what this particular tells you is this green is your goal point. So I have defined here. So my start states are 0, 0, 0, 20 and 621. I hope you can see that, right? So my 0, 0, 0, 20 and 1621. This one. I don't know why it's in yellow, but yeah, 621. So these three pairs my start states. My goal state is 9, 5. This green one is my goal state. So I want my agent to start from any of these 3 points and reach the green one. Now, what are the rewards of each and every cell in this grid world comes from these 2 and 1. So I have not written the negative term, but what it means that the states which you see are 2. The cells which you the cell in the grid which you see is 2. It's actually, if it goes there, it will get a reward of -2. Hence the red. Hello?
Yeah, understood.
And if you see these -1s, right? These -1s are a little bit, -1s are okay, then -2. So these are covered with pink, not too red. The remaining are zeros. And even though the goal is in the -1 cell, but since it is the goal, that is where we need to reach. So we have given it a reward of 100. We will define the goal reward as 100. So goal reward is 100. Remaining all states are according to this. So -2s, -1s and zeros. Okay. So yeah, I hope. Yeah, this yellow is the current state where my agent is. Yellow denotes where my agent is. Blue are the start states. So this also is one of my start states. Green is where I need to go. The more the red that the grid is, the more I need to avoid those states. Okay. So first, let's just initiate the Q values, right? So initiate the Q values. We'll just initiate some Q values, and so what you see here is you have started with some policy. So you remember value iteration, policy iteration, where we initialize all the Q values and we start with some policy. Say all the policies go down everywhere, irrespective of whatever state you are in. I don't. This is my starting policy. Okay. So now. Just now I stated that in Q learning in SARSA. So first we'll do SARSA. So SARSA, what you do is initialize Q, all the Q values for all the states. Okay, so I hope you guys don't have any doubt how I'm going from Q to policy, right? Once I initialize Q, plotting Q is I'm using epsilon greedy or not epsilon greedy. I'm using the greedy method to come to a policy, which we did in value iteration and policy iteration. That is clear. Exploration strategy. So once you have initialized your policy, you explore. So how do you explore is first you pick a state S, you get a state, and then the action that you pick from that state, you pick epsilon using epsilon greedy or softmax. Any one of the exploration strategies you pick, and you pick that state and you do exploration. Once you do exploration, you get a you generate a sample. You go to some next state, ST plus 1, you get RT plus 1. Once you get XT plus 1, RT plus 1, using QS t plus 1, your previous estimate, but for now for the new state, you again pick an action at plus 1, again using epsilon gradient or softmax, and then you update it in the SARSA equation. QST plus 1, QST at new. This, the left side term is, this is the new one. There is the old estimate plus alpha into the reward that you have gotten for that one sample path, gamma into the Q for the state which you have gone to, and at plus 1 is the new action that you have picked using epsilon gradient or softmax minus QST. I hope this updation is clear for SARSA, right? But why am I writing, why am I using exploration strategies is to pick 80s and 80 plus 1s. I hope that is clear. So these two codes, one is for epsilon gradient, one is for softmax, just to choose an action so that I can update my Q values. Okay. Like if you are lost, you can just ask me. No issues. So hyperparameters. So yeah, we have some hyperparameters. We have some hyperparameters. So you know alpha is a hyperparameter which, yeah, so we have, I have taken it as point, we have taken it as 0.4, gamma is 0.9, and okay, so total number of episodes, I'm capping the total number of episodes at 10,000. So I don't want it to search till infinity, I just want it to search till 10,000. Once it's done 10,000 search, I'm telling it to just stop. Don't search more than 10,000 steps. Yeah, and epsilon, for epsilon gradient, epsilon I have taken it as 0.1. Okay, so let's implement SARSA. So yeah, so this is SARSA where yeah, so you input the environment, the Q, initialized Q function, gamma. Okay, this plot it, I will show the plots and all. You have the update equation here. Q state 1, state 0 action, alpha. So this plus is equal, you are updating this value by adding it to the same thing, plus alpha into reward plus gamma into state of next action minus the state of the previous action, and then you are incrementing your steps, taking a look at the steps. If your steps exceed 1000, you stop, and yeah, every so here I'm doing for every 100 things I'm plotting the plot. Now I'm plotting the plot. So this is my initial plot, right? Okay, so now you have seen that here at what episode I am numbering is showing in the bottom. As you can see, the heat map is changing. So previously it was all down. Now you can see that the policies are updating at each step. This is the goal where it needs to go. I hope my cursor is visible.
Yes.
And this is the region where it needs to avoid. So the heat map is trying to take it to a trajectory with more probability that it will avoid this area and go and avoid this obstacle and go through this and come through this. I hope that intuition you are getting. But remember, there's always stochasticity in the environment that any action you take with 0.5 chance you will just get pushed to the right side. So there is no deterministic optimal policy like we did for the value attribution policy. So yeah, so as you can see, if it is somewhere here, it's not trying to go straight through the red region to this thing. It's trying to go far away from the red region, and then it's trying to come back in this trajectory. I hope you see that.
Yeah. Right.
So it's not actually that it will not actually converge to the exactly, because I've just run it to 10,000 episodes. I've not run it to more episodes. But this policy, it will like it's a somewhat a good policy. It is not allowing it to go to the red region, and it's doing. So let us visualize this policy. So what I'm going to do is I'm going to, now I know the policy, right? I know the policy. Now I'll run one sample path. Okay. So So take a look at. So it started here. There look. The optimal policy, if there was no penalizing here, would be to just go straight through this, but it's trying to avoid this, so it's going above, and the right shift that you're seeing is the wind blowing it to the right. So maybe we can do one more sample. The optimal, the policy remains the same. The policy is trying to take it above that obstacle and reach the green path. It's not trying to directly go through the.
Yeah.
And there is also stochasticity in the action also. That is why it is going into the red part, because with 0.2 probability, it will not take the action which you have told it to take. We'll run 2-3 more samples so that you get an understanding of. So yeah, analyzing. Okay, this will take some time, but I need to show the plots for it. So yeah, if you guys have any doubt, you can ask me in the meantime, because this is going to take some time. Maybe I should have not did this, but this is needed to show the how much episodes it's taking to reach. Okay, so this is just analyzing all the different possibilities of SARSA for different experiments, and it's just plotting these number of steps to goal in the total reward that it gets. So once it reaches the goal position, you'll always get 100 reward. Next is Q learning. So it's the same thing, but the upgrade information now instead of just taking the next state, you're taking max over all. You're appending that max.
So I think your screen has frozen. Also, your voice is choppy now.
Oh, okay. My screen has frozen. Is it now moving? Hello.
Yeah, it's moving.
My voice, is it fine or is it still choppy?
Yeah, voice is fine. Yes.
Okay, actually, I think what is happening is my system, my laptop is not able to take all these, like, parallel it's running these experiments, parallel it's sharing the screen, parallel I'm recording this video. So I think that might be due to this. Maybe I'll not do this for the Q&A part. In the Q learning, instead of selecting the action again using epsilon greedy and softmax, you just do it. You just maximize. You do it greedily over all actions. So in a sense, you can say that it's better than SARSA, but it depends on what you're trying to do. So again, we'll plot the heat and we'll do a sample part, and we'll compare SARSA and Q learning. Since this is just a pi problem, well, not much to compare, but yeah, you get the intuition. I hope you get the intuition. I think that is. I thought of again going for the deterministic setting, but once you go back to the deterministic setting, it will be very simple, where you understand what is the optimal strategy and it will converge very quickly. Same as value function and policy iteration are going. Policy iteration took 3 steps to converge or something. There you used V function to calculate. In SARSA and Q, you use the Q function. In the Q function, since you have a term A which also you need to calculate, so you explore using epsilon greedy or softmax to come up with the next state here, to come up with trajectory for the next state. I hope that is also clear. Like, I hope I'm not confusing you more with comparison with value iteration and SARSA and Q learning. Okay, so this is just plotting now Q learning. I'm plotting the heat map for the Q. Okay, maybe I forgot to initialize the Q again, and I just took what was in SARSA and chuckled it. Again, maybe, yeah. Yeah, but okay, but Q learning also, if you start from the same initialization which you did with SARSA, you'll get the same thing. But here also you can see again the heat map, which one changing. In Q learning and SARSA, you also have the problem which you face in value iteration. Do you see that? Like in value iteration, you have the problem that your values kept on changing, but then your optimal policy, when you come back to the policy with greedy setting, your policy was fixed. So there was a problem of when to stop value iteration. Similar problem is there in Q learning and SARSA also, because you're just updating the queues. You don't know when to stop the queues, but updating of the queues. But you could come up with a situation where your queues are changing rapidly, but your optimal policy remains the same throughout. This is for Q learning. Q learning, the moment it's going close to the red part, it's coming down. So I think this is because I have initialized Q learning with the SARSA. So it's better than SARSA in this case, but if both were initialized with the same plot, then I think this wouldn't have happened. But now you see that it's completely, it's like trying to go away from the red. Yeah, so I'm skipping this part and just logging the previous thing which I had shared and that's it. So this, since is a toy problem, there's not much variation in sample level. But I hope you understood the implementation for learning in SARSA. If you have any doubts, you can ask me. I have 5 more minutes remaining. I'll put this code file in the NPTEL extra teachings or some materials is there, so I'll put it there.
Okay, yeah, thank you, sir.
Yeah, you guys have any doubts or any feedback about it? Like more theory or more code?
Yeah, I feel like I find code more instead of theory. Yeah, code is more understandable,
Okay. So
practical.
so till last I was more into theory. Then this is the first time I'm trying to introduce more code. I think someone else said the same thing. Like code would be more efficient. But the problem with code is I can only show you one sample path, and one sample path could be very notorious. Like one sample path it might not do what it wants to do because of the stochasticity in the environment. And you'll be like, "Arey, yaar, it's not working properly." But actually, it's not working properly because there is this underlying stochasticity in the environment. So I hope that comes forward.
Yeah.
That makes sense what I'm saying. Like while we did SARSA, there were times when the agent went to the red, but it was not because the agent wanted to go to the red. The agent was taking actions not to go into the red, but then you have that probability point to where it would take an action which you have not given it. So and point 0.5 pushed it to red, and those two stochasticity made it to go to red. It was not that it didn't come to an optimal policy. The optimal policy was to try to stay as away from red as you are. But then if you're lucky so bad, twice or thrice you could sample from that point to probability and pick the worst action that is possible.
Yeah, right.
Yeah. So that's why I showed 2-3 sample paths and yeah. And here I think I initialized the Q learning with the end of SARSA. So
SARSA.
yeah. So you can see that I think Q learning was better in the sample paths which it got. It was very trying to stay very far away from the red part. So I should have changed that. Maybe I'll do that and I'll put it up in the the team's NPTEL G drive folder that they are sharing with us.
Yeah. Thanks. Sir, one question. So, do we have any reference book for this practical code learning kind of like I tried to search, but most of the books are theoretical one
Okay,
on
yes.
this reinforcement topic.
Yes, so most of the books are theoretical. Even the parts that I did were theoretical. If you want code, okay, there is a nice platform for Gym. Have you heard of Gym?
No.
Okay, just a minute. Let me just